just friends, lovers no more. Just friends, but not like before. To think of what we've been and not to kiss again seems like pretending it isn't the ending. Two friends drifting apart. Two friends, but one broken heart. We loved, we laughed, we cried. Suddenly love died. The story ends, and we're just friends.
Hey folks, how's it going? Let's see. Get these things put over here and then get this thing. All right, compiling. Let's see. Today we're starting on something brand new. And that's because this morning I merged the last of what I was working on with the new C++ DSL that Jank has. It works now for types and for values. So if you wanted to, for example, if you wanted to access some template instantiation that has a value inside of it, now you can just do that using this DSL. If you're in value position, then we'll expect a value. If you're in type position, we'll expect a type. So if you want to get a function, here we have numeric limits, long. We grab max out of that and then we call it. First you have to, this is like the copy fucking icon is really annoying when I'm trying to show like different parts of it. But first you have to grab the max function. So we instantiate the template for standard numeric limits. We get a long int. We get the, we say we want the member of that called max. That gives us the actual function. And then we have the surrounding parens that actually call that function. But if you wanted to just store like the pointer to the function, then you could also just do that. Like this will just give you the pointer to the function. Yup. And even like crazy shit like pointers to members. So if you want the address, which is basically the offset of this first member inside of standard pair, you notice there's no like instance here. This is just the type, and so this gives you an address to this member, which is basically an offset, and then you can invoke that. It basically gives you like a function-like thing that you can then invoke, given some instance of a standard pair in bool, and it will then that function will return you that member. It's a really neat way that C++. Well, I mean, it's like the syntax and everything's fucking crazy, but it's kind of a neat way of having like it's kind of like a higher order members. I don't know if that makes sense. Because like basically it's just like you can pass around pointers that are like functions that when used on a type, I don't know, maybe they're like lenses in other languages, in like more functional languages. This kind of gives you a lens into this member called first in pair. Anyway, all this stuff, we have this DSL that works for types and values. All that's done and merged in and part of the jank book, which means that today we're not going to spend all of our time talking about this because I already talked about most of this last stream. The value stuff is new. And the syntax, like for doing this, now we just use the tagged CPP for both types and for values. Although you don't have to do it for a type if it's in type position. So if you're doing like a CPP new or unbox or whatever, the first argument they expect is a type. So you're automatically put into DSL mode there. So waiting on ads and then telling everyone what we're gonna be doing today. What are we doing today? We are doing optimizations. Today we're doing optimizations. Well, today we're starting down the long journey, the long fucking road that's gonna be months long of turning jank into an optimizing compiler. Right now, today, and for the past few years, this iteration of jank, I would not call it an optimizing compiler. So we try to do a couple of things. We try to do a couple of clever things, you know. when we're doing code generation, we try to elide some things when we know they're not needed. But we don't have like the typical optimization passes. We turn things into there are a few terms that we can talk about. So there's this anormal form. We turn things into anormal form when we're doing code gen, and that's just kind of like a result of the code gen. This is kind of like a very mathy explanation. We have a similar explanation at the top of our C++ generation, where basically we say like, oh, okay, so if you have this print line where first argument is a call to thing, second argument is an if expression, then we flatten all that out, right? And so first we do thing, we put that into its own temporary. Then we have an expression, or then we have like a value for the result of the if. Then we do the if, and each of these just ends up assigning the value for the if. And then once we have all of that flattened out, then we'll just do the print line call with those values. So this is basically like the anormal form. We're doing this already for C++ code gen, but we want to do this in an IR level. So what we're going to be doing is we're going to be building a new IR for jank, and IR means internal representation. So LLVM has its own like LLVM IR, and then there's people are working on like a higher level Clang IR. We're gonna be making our own IR, and so we're gonna take our AST, we're gonna convert it into like this anormal form, which is like flatten out all the nested shit, And then I'm going to throw another term at you guys. Then we're going to do a control flow graph. CFG is what they call this in the compiler world. So we have A normal form and CFG, and basically a control flow graph is a common compiler representation. It's not the only way that things are done, but it's a common way that things are done, where you split your code into blocks. They're called basic blocks. We have these right here. And so we're just I'll show you this example that they're showing here. It's the first time I've seen this one, but but we'll walk through it. So we have this function. This is a C function, and it takes in a C string, and it prints that C string with parens around it. But it only conditionally prints the string if the pointer to the string is not null. And so we have this. This is an interesting case because we'll end up with 3 different blocks here. We have a block right here that also includes the check, and now the check is going to determine which block to go to next. And so we're either going to go to block number 2 next, or we're going to go to block number 3. And so they have it written out in this way, like that's still written out in C, but still like actually breaks it into the blocks. And yeah, so it would look like this. Okay, block 1, which is generally called entry, is just going to unconditionally do our open paren. And then we're going to check if P is not equal to null. If so, we're going to go to block 2. Block 2 unconditionally prints and goes to block 3. And if P is null, then we're just going to jump to block 3. Now, the nice thing about breaking these things into blocks like this is it really simplifies the understanding of control flow. So control flow graph. You get an idea of like what leads to where and why. And in particular, with CFG, each block has only one terminator, and so you can jump back to, like, you can jump into different blocks, but each block, like you can jump into blocks from previous places, but like each block only has one terminator at the end. So that's either a return, or it's some sort of conditional jump, or it's a throw, or something like that. Here, this is showing the same sort of thing in LOVMIR. So like this is what we do when we do IR gen, and the IR that we're gonna generate for jank is gonna be something like this, but we're actually gonna use closure data. And so that way we're going to be able to operate on our IR as closure data. We're going to be able to serialize it and deserialize it as closure data as well. That's going to expose it to closure tooling, which is going to be super fucking great. And it's going to allow us to write just sort of like pure data style transformations, pattern matching, that sort of stuff on our IR. And I'm going to go a lot more into like how that's going to work. But anyway, so control flow graph breaks this stuff up into blocks. Blocks have a set of instructions. So this block has 1, 2, 3, 4, 5, 6 instructions, right? And then instructions are implicitly ordered. That's just the way the control flow graph works. There are other ways of representing these things like sea of nodes, but we're not going to do that. We're going to do control flow graph. So we're going to need a bunch of blocks. And so this function basically is going to have like an array of blocks. And then each block is just going to have like one terminator that jumps to the next block. And then there are some special ways that we're going to need to deal with conditional values, and there's a phi node for that, which we'll go into, but we're not going to go into yet. And then all of this is going to lead us to SSA. I don't know if I search this, it's going to be Social Security. There we go. So we have three terms that I'm throwing at you here. Twitch TD. Why am I using my own IR instead of using LLVMs? Is it about being standalone from LLVM? No, but I will answer that. Good question. I'll answer that. So the third final term I'm throwing at you here is SSA, which is static single assignment. And basically, this is a representation in the compiler that is going to be pretty straightforward for us, but is a lot more complicated for languages that have mutation. And basically, the idea is that you have a representation in your IR where each value is only assigned once. And so, for example, here, like y is saying, okay, so y is 1, and then also y is 2, and now x is y, right? And so we know from reading this, like, all right, x is 2, got it. But this is not SSA form because y is assigned multiple times. So SSA form would say, okay, y1 is 1, y2 is 2, and x1 is equal to y2. Now we can do some really great things with this, right? So first off, we can look at this already. We can look at this SSA form and we can see that y1 is not used, right? That allows us to just completely remove that. You could figure that out more indirectly by looking at this before and say, oh, it's assigned and then it's assigned again without being read. But SSA form just gives us that already. There's no reference to Y1 anywhere. It's dead code. But this allows us to do a ton of things. So there are examples here. But yeah, you have like peak hole optimizations, which are not as dirty as they sound. People optimizations, not as dirty as they sound. And dead code removal, constant folding. We're going to be doing the elision of var derefs and common sub-expression optimization. We're going to be doing a bunch of stuff. All like the classic things, jank we're not doing anything out of the ordinary here. We're just going to do the typical optimization pipeline. Now, why are we doing a custom IR instead of LLVM IR? The answer to that is LLVM IR is very low level. In fact, so this is LLVM IR that we're looking at here. LLVM IR is so low level that Clang is adding its own IR. So there's this whole Clang IR project. And it's meant to, and so we can see our helpful AI summary. It's designed to better reflect the features of C and C++, allowing for more efficient analysis and optimization. Now, the reason why this is a thing, can we see this? I just wanted an example of how this looks, but unfortunately the docs don't give that to me. But anyway, Clang already has come up with their own IR because LLVM IR is too low level, right? You get by the time you get to LLVM IR, you've lost a lot of information, and there's no way of just embedding that information. And so Clang wants a way to represent their IR at a higher level. And the thing is that jank is even higher level than Clang. And so I want to be able to represent things like var derefs in my IR, like have that be a first class member of the IR, and also things like trait conversions, dynamic calls versus static calls, and all of the like closure-y things we do that are unique to the way that Clojure works with vars, with interning of keywords as well. All of these things are higher level, way higher level than LLVMIR. And so trying to do things like say, okay, well, we've already derefed this var in this function. We don't need to deref it again, even if we access it again, would be very difficult, or at least a lot more difficult in LLVMIR compared to our own IR. So we're going to be able to choose the level that we want to operate at, and we're not going to be worried about bits and bobs. So LLVM is very like, oh, load this, I32 from memory, store this I32 in memory. That's very low level. And so our IR is not going to be operating at that level. Our IR that's really difficult to say, our IR together. Say that 3 times fast. We're just going to be operating at like the Clojure level. And so another way to think about this, there's a sort of mind-blowing way to think about this. We do need a name for the jank IR. I just have a hard time saying IR, it seems like. When you think about what jank's IR is going to look like, now this is not yet designed, but I will show you a glimpse anyway of sort of what I have in mind. And I'm going to be working on this for a while, for months. So I'm sure you guys will see a lot more of it. Imagine that this is a basic block, and it's a basic block of operations. And so I imagine that our IR is going to be something like var deref, defer, and then we're going to have like a Clojure core print line, right? And so this is going to represent an operation that takes this var, derefs it, and then we're going to need to like, I guess we're going to need a way to like put this, it's going to need to go somewhere. So it would go into something like V1 maybe. And so here we're basically introducing a value, and we're getting this value from doing this thing. And then if you wanted to do like a call on this, then we would have like a dynamic call on V1. And I suppose we should do this. And then we would have args. So if we wanted to call print line with, let's say, a keyword, would be something something like this. Foo I don't know. I'm shooting from the hip right here. But here we could do something like v2, right? And so this would basically describe the code that does this. Now, the nice thing about this is, so this is SSA form, and also this is CFG, and then that all implies a normal as well. And so we would say, all right, let's get our v1 is going to be this var deref. We have a keyword we're interning as well, and then we're going to do a dynamic call on. I guess we need the function, which is our v1, like so. So the nice thing about this is we're going to be able to dedupe these var derefs. We're going to be able to dedupe the keywords that are being interned, lift those up. We're going to be able to do things like inline calls and everything like that. And then we're going to be able to do things like, people optimizations are like pattern matching. Peephole. It's not here. But basically we could do pattern matching on this so that we know, like, okay, so if you're calling plus, this is a very common optimization that compilers do. So like if you're calling, so they'll specifically say like, all right, if you're doing plus with two literals, then just replace that entirely with the result. And so this would just be replaced entirely with 12. And the way that this is done generally is, TwitchD, like one way to do this is actually comp time or partial evaluation. Like one way is to actually evaluate that. But most compilers for like static languages, when they're doing this, they don't just go evaluate that because they don't have JIT compilers, you know, they don't have an interpreter even. But they know that like they have a plus operator and two literal values. They can just sum those together and replace the plus operator with the sum of those values instead. So it's easier actually for jank because it's a closure we can generalize. And so rather than just saying like, okay, so here's plus, and so like, I was just watching a talk on like Go and how they did this, and they have a whole set of like rules that are basically pattern matching that say like, okay, so if you have like a, I don't know how they represented it, but like they're like, if you have a plus and then your first argument is some like literal integer, and then your your second argument is like a literal integer, then they'll have like, so this is like the match that they do. Then they'll have a special branch that says, okay, then if you match this, then replace this instead with just the literal integer, which has an updated value. And the value is then, you know, they'll call a function that sort of can be invoked with each of these, and then we'll give you the updated thing. We can generalize this in jank because we have JIT compilation. And so what we can do is we can just know which functions are pure and which functions are not. And we can know that because to start with, we can annotate all of the Clojure core functions, whether or not they're pure. And basically every other function in your program is either a composition of the usages of core functions, or it's doing interop. Like that's Clojure programs are either built on like using core functions, or they're using interop, or they're using existing functions that were ultimately built on either using core functions or interop. And so if we just imagine like, okay, if you do interop, then the function is impure as a simple like starting case. But if you only use pure Clojure core functions, then your function is pure. Can you annotate pure versus impure functions outside of jank core? You could, but the thing is you shouldn't need to. If you're doing interop and then you still want to say, but by the way, this thing is pure, then yeah, I think you should be able to. And then what we can do is then we can say like, okay, so if we have a call to this function and the inputs are all literals, then we can just call the function ahead of time, like call the function at compile time. Now this does mean that if you write fib and you're trying to benchmark that, and then you're like, yeah, fib 30, like fib's a pure function. And so we're just going to evaluate that at compile time. We're going to replace it with the literal. This is a great thing to do. It's a great thing that we're going to be able to generalize this as well. Yeah, there's a ton that we're gonna do here. And that's why it's going to be months worth of work, including we need to actually figure out what the fuck our like what our SSA is going to look like, and which things we want to be first class, like var deref and dynamic call and intern keyword, and then which things are just going to be function calls. And okay, before we get to coding, and I only have 2 hours today, and then I have an appointment I got to get to. So 90 more minutes. But before we get to coding, when you look at this IR here, and this is, I mean, it's not figured out yet, but this is roughly how it's going to look. This is a pretty good idea how it's going to look. You can kind of start to see this as a bytecode, right? Now, sure, like this is a text representation. It's not actually in some sort of like encoded binary format, but it is a text representation of basically bytecode. And so you can imagine that this is kind of analogous to Clojure's generating their own JVM bytecode. To the point where, like, we could just interpret this SSA like Ruby VM or Erlang VM or the JVM, right? Java Virtual Machine. And we could just interpret this this IR in the same way that a normal VM would. There's nothing that stops us from doing that. We're just like, we're going to JIT compile it. And actually we're going to do I have some plans to completely change the way that we code gen once we do this IR. That should be pretty fucking amazing to investigate as well. So yeah, I'm hoping that by the time we get done with all of this, jank is very different and has very different performance profile as well. But I wanted to point out that like you can think of this as a bytecode. And so as I was chewing on this, I was wondering half seriously, like, oh, should we call like the execution engine for this, like the compiler, the runtime, the interpreter for all of this? Is it the jank VM, aka the JVM? And so jank has its own JVM. And so jank is closure running on the JVM, but it's a different JVM. And then I thought, no, I won't call it that because that would be mean. That would be harmful to the sanity of everybody who's doing anything jank related. But Twixty, you're right. We need we need some sort of name for this IR. For now, it's just going to be jank IR. Sure. If we come up with something better, if we come up with something more clever, then we can use that. So, what does this mean for code? What do we have to do for code here? Well, the way that jank works now is we have a lexer, we have a parser, we build an AST, and then we either code gen that AST directly to LLVM IR, and we have 7,000 lines of code set up for us to do that, or we code gen all of that into C++, and we have 3,000 lines of code that does that. So my plan here is instead of going from our AST to either C++ or LLVM IR, we're going to go from our AST into this IR. And so the AST, like its job is going to be to make sure that everything type checks and the whole program is correct. And then as soon as we know it's correct, or not necessarily the whole program, because Clojure works at, like top level form at a time, but all the code going through the analyzer with the AST, we just need to know it's correct. And as soon as we know it's correct, we transform it into SSA form, into this IR form, and then we massage the hell out of it. We do whatever we want to optimize. Now, of course, it's the optimizer's job to make sure that the behavior stays the same. As long as the behavior stays the same, we can change whatever we want. And then we have the question, hey, Fromnophobic, intermediate extended representation. Maybe not that. I hope you're doing well, man. But we have this question of, okay, so once we've gone from our AST to our IR and we have optimized the hell out of that IR, done we're going to do a bunch of different passes on that. Then what do we do with it? Our current code generation for both LLVM IR and C++ only works with the AST, which means we're going to have to do whole new code generation. And that is in some way bad because it means we need to do whole new code generation. But in some ways it's good because we get to revisit how we want to do code generation. And the current plan, I don't know if this is going to work, but I just want to spell out my plans because I know like I only do these streams once a week. And part of that is just me like conveying what I'm up to, right? And showing the thought process, putting the thoughts in your guys' minds, and then, maybe getting feedback on that. But the current plan is that I will not do either C++ gen or LLVM IR gen. The current plan is that we go from our AST to our SSA, we optimize the hell out of our SSA, and then we skip C++, we skip LLVM IR directly. Our code gen is actually going to be generating Clang AST. We're going to generate Clang AST. So we're going to walk through our IR, and we're going to generate Klang's AST nodes directly. Now, the reason that we do that is that it's like generating C++, except if we generate C++, then what we have to do is, so first off, we do all the string building, we generate all the C++, and then we give the C++ string, all of that C++ code to Clang, and then Clang parses it and builds an AST out of it, and then proceeds to optimize that, and then generate its own IR from Clang's AST. And so what we're trying to do here is we're trying to cut out the middleman. We don't need to generate C++ so that then Clang can parse that C++ and get to its AST form if we can just generate Clang's AST form. So this should hopefully lead to pretty big compile time wins, because we're not going to need to generate and then parse all of that C++. But then this leads us, fromophobic. Is Clang's AST stable? No. Clang's AST is not stable. And so, but I'm not the only like jank isn't the only language that's done this. Swift also builds on Clang's AST, maybe even Objective-C and Objective-C++. Yeah, I think I think Objective-C, Objective-C++, and Swift, those Apple flavor langs, all sort of build on Clang's AST in the same way. Now, it's different for them because obviously Apple is a big company behind the work on Clang. But I think that we're already using Clang's AST a lot. So this wouldn't be the only thing that we're using it. Like jank's C++ interop is done using Clang, very, very directly. So if we jump into here, like find best, or so like for example, like overload resolution. If we have a bunch of function candidates and we have some argument types, like this is straight up like Clang code to like synthesizing code RAII and like expert value kinds and qual types and source locations and like all of this stuff is already Clang code because we're using Clang to do all of our interop. That's how jank is a C++ dialect, is that it builds on Clang and uses the C++ stuff in Clang. And so this is basically just we're just leaning into that. So is this going to cause issues down the road with Clang having breakages? Maybe. But what I'm going to do, to mitigate that is we're going to, well, first off, we're going to try to see if this can work, right? I don't know how difficult it's going to be. I don't know if it's going to be viable, but we're going to try it. And I'm going to chat more with some Clang devs to get their input on it. But I think it's viable. I've thought about this for months at this point. Like it's not a new idea. And I think it's going to be viable. But we can try to tie jank, to certain Clang versions. That's going to help, rather than just saying, oh, we're going to work with any Clang version. It's like, okay, well, jank works with Clang 22, and we're going to need that, and then okay, this version of jank is going to work with Clang 23, and this version. And it's like maybe we even go lockstep. I don't know. So that does. It has implications, but we're gonna see how good it can get. Like if it has really big compile time wins, then that may be worth it. Because I can say that right now, like all of the C++ code that we generate it's really a lot for Clang to handle. And the thing is that jank isn't even using, like, people aren't even using jank for like large real world projects yet. You know, I'm only compiling like Clojure core, which is, to be fair, is like 8,000 lines of jank code in Clojure core. But 7,000 lines, 8,000 lines, whatever that is nothing compared to, you know, like 100,000 lines of like a real world, let's say game engine, you know, or something like that in jank. With the way that jank works now, that 100,000 lines of jank code would be millions of lines of generated C++ code. And then, you know, like trying to JIT compile all of that, or even AOT compile all of that, it's a lot, because C++ is one of the slowest languages to compile. So I'm hoping that skipping through all that allows us to make jank more scalable. But it also solves some big problems as well. If we generate C++ code, then we need to worry about source mapping. And right now, jank doesn't do that. So when you're in a debugger and you're taking a look at like the function that you're in, it's gonna say like, okay, well, you're in this C++ function, right? Or the stack trace is gonna show some C++ function and the source info for that C++ generated C++ code. But what we want is to actually point at your original jank code. And so having an additional source layer in between makes that more difficult as well. That's not necessarily insurmountable. I think it is something we could do if we need to generate C++ code, but I think it will be easier if we're able to use Clang's AST directly as well. So this is the current plan. That is like getting to the point where we're doing that code generation is, or that where we're doing that like Clang AST generation is going to be probably like at least a month away. Because I think we're going to have a lot of this IR, like CFG shit that we're going to need to do in between now and then. But I think when we get there, generating Clang AST is going to not only bring jank closer to C++, which is what we want. We discussed last stream how jank is not only a Clojure dialect, it's also a C++ dialect. It's not only going to cut out the middleman. It's not only going to improve our source information. It's not only going to make sure that we generate correct code rather than just string generation. You know, we're actually generating like AST nodes. But also, I set up this sentence, like I'm listing a bunch of things, and then the structure of the sentence is, but also, and then another thing, but I don't have any other things. But it's going to do all those things. And if that doesn't work out, then we'll go back to generating C++. But either way, going from our IR, we don't have, like, we're not going to have code gen. And the code gen that's written right now for C++ and LLVM IR, that's going from the AST. The code gen from our IR is going to be quite different. And so we really can't use that code gen that we have right now. And so even if we were saying, oh, okay, well, let's still generate C++, we're going to have to rewrite like all that code generation for C++ to go from our IR instead of the AST. So it's not like we're saving ourselves anything for that anyway. Cool. So all of that is explained. This is what we're doing. We're turning jank into optimizing compiler. We're going to get things into this CFG format with basic blocks. We're going to figure out all of our instructions. We're going to represent them in SSA form. And then we're going to, I think before we add any optimization passes, probably, then we're going to figure out the code gen. So that way we can actually have something that works. And then once we have code gen working, then we're going to start adding our optimization passes. So got to figure out the IR first, then get the IR working with whatever sort of code gen we're doing, and then work on optimizing the IR. So that means it's going to be quite a bit of time before like this is actually making jank faster, because to start with, it's just going to make jank not work until jank finally works because we have the IR, and then whatever code gen we have, hopefully to Kling's AST. And then we can start optimizing the IR. Okay. So to get started on this, we have the such trivial, such basic beginnings. We're going to get started with a branch. It all starts with a branch. Frodo leaves the Shire with a branch, with a twig in his hand. What is our thing called? I'm going to call it, I call it SSA. Do I call it IR? IR is too short for a branch name. Optimization. Patty. That's a great name. Where is my mouse? My mouse is frozen. Huh. My keyboard, my USB switch for my keyboard just switched for some reason and started typing into a different computer. Patty, because it goes in the middle. That's great. Hot dogs also go in the middle though, right? I was trying to type SSA. Okay. Nice. Branch is made. I think we can probably call that for the day. I don't know about you guys, but I know a productive day when I see one. All right, so we're going to make some new code. I want to call this IR, I think. Yeah, I want to call this IR. We should call the branch IR. I think when I type SS, my fingers automatically want to type H for SSH. And so that's why I get SSHA. Okay, yeah, so we want to be able to represent our basic blocks. That's the first thing that we need to do. And so we need some sort of code generation, or we need some sort of like AST visiting that is then going to generate our basic blocks. So we're going to need to do convert our AST into a normal form. We're going to need to break that into blocks. We're going to need to ensure that that's SSA. Taco T, what's up, man? Or gal? No offense, sorry. Didn't mean to assume. So we're gonna want a processor, which is just what we call like all these AST visitors. They're all processors. So we're gonna have an IR processor. Now our IR processor is going to have, let's start with include. Our IR processor is going to be in jank IR. We're gonna have struct processor. Do we actually need this struct to be in the header here, or can we actually just have can we actually just hide all of that? Early days of jank, I was putting more of these things in the headers, and now that I realize that the cost of this affects not only compile time but also runtime, because we need to load all these headers at runtime in order for jank to be able to operate with the the generated code to be able to operate with the. Oh, fascinating. Fromophobic. I think that yeah. So one of the biggest issues that jank has, like one of the biggest challenges that jank has, is the generation and JIT compilation of C++ code. And we use Clang to JIT compile C++. But it has so many issues, not only around its the way that it deals with precompiled headers, to JIT linker issues, to exponential performance, in some cases. Like JIT compiling C++ is just like a very uncommon thing to do. It's not a well-traveled road. If we were to generate Clang AST instead, then we could remove. Could we remove our precompiled header as well? No, we couldn't. Never mind. Yeah, we can remove all of that generated C++ though. Yeah. And for closure core, we have, what is this? 2. Have you considered starting over, writing everything in Rust? Well, C++ interop would still be doable in Rust, but it would be harder. But sure, yeah, I mean, I've considered not starting over, but I've considered like gradually moving pieces to Rust, which will probably, I mean, jank will probably end up being in Rust eventually. Right now, I can't really justify working on that. But if we imagine that, jank is still a thing a decade from now, and it's in production, and we got big companies using it, I'm not going to keep it in C++ forever. I think, like, we'll definitely still like have all the C++ interop. Jank will still be a dialect of C++. But it doesn't need to necessarily be in C++ for that to be the case. But anyway, I was saying here that, and if that blows your mind, then you gotta be realistic. You gotta be realistic about these things. Like, and if it sounds contradictory that we would have a C++ dialect that's not written in C++, then you also have to be realistic about these things, because C++ is still like such a huge market, and also something like this for Rust is not currently possible, because it would require some sort of like JIT compilation mechanism on the Rust side, which just doesn't exist right now. I don't know if it ever will, because of Rust's borrow checker, and how strict Rust's like compilation model is compared to C++. Anyway, very tangential. So yeah, we generate for Clojure core, we generate almost 5 megabytes of C++. That's unformatted. If we format that into core.cpp, I don't know if core.cpp exists, so we're just gonna replace it. This is like an angry face, which makes sense because it replaces whatever file's there. So not only is this going to take a long ass time, because it's like 5 megabytes of Clojure of C++ code, but also, so let's take a look. Yeah, so we have 145,000 lines of C++ code, just for Clojure core. And Clojure core is, I think, like core.jank is 7.5 thousand. So 7.5 thousand becomes 145,000. And we can't, I don't think that we can get much lower. Like, we can get lower, sure, but I don't think we can get much lower. We're not going to get like an order of magnitude lower with C++, because it's just not expressive enough. So this is one of the things I want to avoid. Now, on the other hand, I don't want to generate IR, LLVM IR instead, because as we discussed before, LLVM IR is too low level. Like, we have the C++ interop stuff. I don't want to generate like a whole, I don't want to do all my own like LLVM IR generation for C++, which does, has its own ABI for dealing with like function calls, and that's not like in a cross-platform. That's not a cross-platform thing. It's done differently on different architectures, and it's just a whole mess. And so this is why it's another reason why just using Clang, allowing Clang to do all of this work for us, is really beneficial. Yeah, or at least could be. We'll see. We'll see. Yeah, but then we had the question of, do we want the struct here? Probably not. So do we need to worry about this? Yeah, probably not. So I'm not going to worry too much about the naming yet. I'm just going to make a function. Our function is going to have a return type, but I don't know what the return type is going to be yet. And basically our function is going to take in our, it's going to take in our AST. And so currently the AST works on one function at a time. Let me take a look. If I go to runtime context and we do this, so eval string. Yeah, what we do right now is for each form, we get a new analyzer. We analyze the form, we optimize it, and then we eval it. So eval is gonna need to no. Oh, and also like optimize here doesn't actually do anything aside from like we strip some metadata. Like this was like, oh yeah, we're gonna have all these passes, optimize the AST, but like the more I learn about this, I realize that like we don't want to be optimizing the AST directly for most things. We want to do we want this IR instead. So eval will stay the same. And then eval so eval for functions. Eval for functions is where the magic happens right now. Where we give the generated C++ code gen, we give that to our JIT processor, and that JIT compiles the C++ code. Yeah. So this whole mechanism is going to change here. So I really shouldn't worry too much about the structure that this has right now, because we're really gonna optimize. Like we're really gonna like rework a lot of the stuff here. So let's just get started with something. So I'm just gonna do something. I'm just gonna do something obvious. I'm just gonna say like build IR, and that's going to take create. That's going to take a single function, and that's why we were looking at eval there. Is that we want to take a single function like this. And do we need any other info? This has the module and the compilation target. Compilation target is either module, a module function, or eval. I think those are going to be needed as well. And so we bring those in. This is fine. Now, what we need here is we need this, and then what is compilation target? Compilation target is here. This is enum. Compilation target is a code gen thing. That's gonna have to move but that's okay. And then finally, I need JTL ref, don't I? JTL ref of struct function. So here we're going to need analyze expr function. I would just, yeah, that's fine. We're also going to need jank code gen Liam processor, which has compilation target. And okay, so here we go. We have all this analyze shit, and then right at the end of this, we're going to have our IR processor. Good. And I need to define this with the correct type, or I need to forward declare it with the correct type. And I need to re-trigger this. All right, now we just have unused parameters. So to start with, this is const, but not used. Actually, you know what? That's kind of the old-fashioned way of doing that. I need to get out of that habit, and so I'm going to force myself to do that. There we go. That should compile cleanly. It does. Okay. So visit. Yeah. So this is basically hey, Robin, why did I have the quotes or the comment around that? Well, because I had a error here that they were unused, and so I wanted to get the compilation passing so that way we could get to linking and verify all of that worked. And so I commented out the name, which is if you don't have a name on a parameter, then C++ will not complain about it being unused. Hi, another Robin. Do we have a third Robin? If so, speak up. Okay, so here we want to visit. So we need to visit our AST. And we visit our AST by doing this visit expression. So we need to recursively visit this way. It's doing some benchmarking, listening to you in the background. All of a sudden I hear hello, Robin, jumped out of my chair. That's funny. That's funny. So here we keep track of the functionality. I don't remember why we do that, but we're not going to bother with it unless we need to. So let's do gen, and this is just going to take a analyze expression. That should be an expression ref. X. Do we need to? Yes, we do need to. What does this return? Which version are you using? Version of what? Are you asking me that? If so, version of what? Oh, version of C++. I'm using 20 with some GNU extensions. So I compile with this. I use some 20 features, like concepts and if const expression in some cases that are very, very, very helpful. How do I wanna go about doing this? I think we need to start representing our model here. So we're gonna have a I don't use I do like almond. I don't get to use exactly the style that I like because I have Clang format enabled, but I have Clang format enabled to be pretty close to almond. But I was not able, despite my efforts and hours of trying over multiple days, was not able to get Clang format to actually like format my code the way that I like it to be formatted. But at least it's consistent. And I'd much rather have like everybody using consistent formatting and nobody be happy about it than for me to get the code I write exactly the way that I want and then struggle to get like my mentees and other contributors to format things the way that I want. So it's kind of the Go format methodology of yeah, well, nobody likes it, but at least it's consistent. You can have your Clang format file and then link it, have it linked in you. That's exactly what I do, Robin. Like this format's on save. So if I put all of these on one line, let's just say I want to do struct function. I put all this like so, and when I save it formats. How does it not work as intended? Well, I mean, Clang format doesn't have options for all the things that I want. So this is like, it doesn't always format code the way that I want it to look. But I'm not able to change that. Like, for example, I have it set to use almond style braces, right? But then why does it use Egyptian right here? You know, why would it have the paren here and then drop this onto a new line? Like that's not how I would want it to be done. Also, like for single line bodies that fit within 80 columns, the way that I normally write it, I would just have them be on one line like this. Now, to be fair, I don't ever do this where it's all on one line, but I would put the body on one line. But Clang format's just it's gonna say, oh, well, you want to use almond? I guess like each of these gets its own line. And so it's just super inconsistent. Like, you know, look, Truthy's done like this as well. Like the way that I would have formatted this is I would have done this. That way all of the parameters are on the same level, and then the parens are used in the same sort of almond style. And it's very clear when the call starts and when it ends, and it's all separated by indentation. And to me, this is the way that I wrote code for over a decade, you know, in C++, before I started using Clang format for everything in jank. And I like that. But I can't get Clang format to do that. Okay, so we have a function, and a function is going to have a native vector of block called blocks, and then we're going to have a block, and then a block is going to have a native vector of instruction called instructions. And then we're going to have instruction, and instruction is going to be, there are a couple different ways that we could represent this. Yeah. Time to write a pretty printer in jank. Man, there are so many things I would want to write in jank, but I have to work on jank instead. If I had it my way, I'd be writing development tools and games in jank right now instead of writing jank, like working on jank. But I still need to get jank there. We'll get there. Okay, so instructions we could model as like a tagged union style approach. Or we can model it with inheritance-based approach. We are going to have a fixed set of instructions. Yeah. We're going to have a fixed set. And we're not going to want to have to use RTTI in order to check for certain types. So yeah, I'm going to go with a variant. Exactly, Robin. Yeah. I mean, tagged union in C++ just means variant, right? Same shit. It's more type safe. So here we're going to start with some basic instructions. And for basic instructions, we're going to we probably just want to start with some things that we know we're going to have. So we are going to need to have calls. We're going to need to have var derefs. We're going to need to have branches, phi. What's the simplest thing we can start with? I think if we start with if we do a return, yeah, I think if we do return let me ask this FP, OOP, or imperative. What do you mean? Like, is jank one of those, or what do I think of those in general, or something else? So we have. I'm going to put these inside of a nested namespace. So ret is going to return a value. And so we need a handle to a value. How are we going to represent these handles? Are they just going to be strings? Which paradigm is my favorite? Functional. I like functional and imperative. I'm not a fan of object-oriented programming. So I like functional programming for some tasks. I think it's really great to be able to, like in Clojure, express things in terms of data transformations. But I also really enjoy doing low-level work. I mean, like my career was in game engines early. I mean, that's how I got started. And I've been in game dev basically my whole career. So I like doing low-level work. I like doing I like making my C++ efficient, and functional programming in general is at odds with that. And so sometimes when I do too much functional programming, like several years ago, I was doing a startup and an esports startup in Clojure that I co-founded, and it was full stack Clojure. We had like a multi-service Clojure distributed backend, and then we had a Clojure script, reframe SPA as our front end. And in some ways it was great, and in other ways I just got sick of writing Clojure. And so I was just like, oh, I want to do some non-Clojure work. And so for that, I ended up writing like an HTTP static file server in assembly for like, I don't know, one weekend or something. And this is simply because when I do too much functional programming, I just feel like doing some like low-level imperative work again. So I don't think I would want to just do one or the other. And that is also why jank is a Clojure dialect and is also a C++ dialect. And so the idea is that you can use jank to do the low-level imperative stuff, and you can just write straight-up C++ functions in jank, and you can ensure that like those functions don't have any dynamic allocations. But also, if you just want to write things the way the way that you normally write Clojure, and do functional programming and model everything around pure data transformations, then you can do that. I think for now, we'll do this. So return has just a value. And then how do we bring in so another thing we can do is if we have like a we do like a literal. Yeah, maybe value is the wrong identifier. So we have a name, and then what do we have for our literal? That's just an object ref. So that would mean instead of, that would mean if this is literal, then it could be like this. So if you just wanted to print 42, then you would have, this was name. Just so I can show you like what I'm modeling here is name and value. And so op comes from the type. So we'll already have that. So we're not actually going to be working with Clojure data directly, but we're going to be able to serialize the Clojure data. And maybe deserialize. I don't know. We'll see. As soon as you start dealing with C++ types and Clang decals and everything like that, then those are opaque things that are going to be harder to just serialize, deserialize. But that's the goal, to be able to do that. So yeah, I think with the return instruction and a literal instruction, we should be able to, we should actually be able to model a function that returns a value. So let's try that. So I have literal and ret, and I wonder, do we need a struct for instruction, or should instruction just be an alias for the variant? Yeah, I think it's probably better to have have a struct for it. We'll call that data. Okay. So a function has blocks. And blocks have instructions. instructions are either literal or return. A literal introduces a name. We should just use name consistently for all identifiers. Literal introduces a name and then has a value. And then the return instruction returns the name of an existing value, or returns the value by name, I should say. So I think every identifier ends up having a name, or every instruction ends up having a name. Probably. We'll see. And then maybe that pushes us away from variant and toward inheritance if there's like common stuff we want to share. But for now, this is okay. Let's see. So, code gen, object ref. We need runtime on that. Right. Now, what do we actually build up here? So we want to make a function and we want to fill that. We want to fill that function. We're gonna have a inside of this expr function, we have the arities, and inside of the arities we have the parameters and the body. So we're going to have one function for each arity. So what we should do is for auto const arity in, and also like what is arities? It's a function, it's a native vector. So we're going to need a reference in function arities. Yeah. And so that means that we're not returning one function. We're actually returning a vector of functions. Is there any other way that we want to model that? I don't think so. Which means that this ends up being a native vector of function. Which means that we need to move all of this into the header because we need to know how big a function is. Okay. And we don't know about variant here. Good. And then, so for each of the arities, we're going to create a function, and then we are going to So we're not quite here yet. What we're going to get back when we visit, is it going to be a single instruction? No, not necessarily. I would say maybe we don't actually try to pull out something like that. And instead we take a context probably. Yeah. I think it's probably easier to just start writing this out here and then worry about factoring it out later. So we build our function and then we want to loop through the body. In the arity, we have our body. And that has a bunch of expressions as values. So arity body values. And those are expressions. So to start with, we're gonna want to add an entry block. So blocks are gonna have a name. Should that be an identifier? I don't know yet. Yes, it should. Blocks have names. Yeah, because blocks can be like values as well. Like when you branch or whatever, you're talking about identifiers for where you're going. So blocks have a name, functions have a set of blocks, and now what we want to do is we want to add our first block. And so we'll say function, and then for some reason my LSP has completely died. I'll try to restart that. But function has, let's pull this out into here. So that way that works. And function blocks in place back. And we want a name. I'm not going to trust this error. Untrustworthy error. Unused expression, and also, yeah. So we are going to have this funds. We're going to return funds. And then here we're going to move fun into there. And then the only thing we need to worry about is this expression. And so we're going to have a block. That's the current block that we're working with. So the way the LOVM-IR does this, or like the way the LOVM like has all this work, is that they have a builder. And that's one thing that we don't have right now. And the builder provides a handy DSL to where you can just like create instructions inside the current block. And so the builder remembers, you know, it keeps track of the block that you're in, and then just allows you to create instructions, and it appends those instructions to the end of the block. And then you can create a new block, and then you can point your builder at that block and then just start creating instructions. It'll always just be appending to the end. So I suspect that we probably want to make a builder, and our builder doesn't need to be visible in the header. So the builder is going to have a pointer to, I'm going to say the builder has a pointer, which is a JTL ref. And it'll have a pointer to a block. And then it's going to have functions for creating the different things that we want to create. So identifier and name. And then so here, this would just say block, and then in place back. And here it's going to make a return instruction. And so the way that we're going to do that is we have instruction here. Blocks have names and instructions. We're taking our block, we're dereferencing it, and we're saying instructions in place back. And then we're creating an instruction and then the data inside of that. So we're going to need to give it inst ret with name, like so. And so here we can make a builder, and we can initialize our builder with the address of function blocks back. And we just emplaced one here, so we know that there's one there. And so if we just disable this, now what we can do is we could just do a b ret and foo. This should compile. $28. Yeah, that's fair. Thanks for the follow, Robin. I appreciate you. So this will allow us to create return instructions. Now, what we want to do, I think pretty early on, which might just mean right now, although how are we doing on time? All right, I have to go in 13 minutes. Let's see if we can get this going. LSP is still unhappy. That's fine. So what we want to do is we want to create a way to serialize these. And I think we want to do that early. That way we can just be printing these as closure data as we're figuring all this out. Because right now we're just building up a bunch of C++ objects in memory, and like, yeah, here we have a function as a block, and that block has a return instruction, but like we can't see that. We can't see that anywhere. So let's print. Let us come up with a printing mechanism. So functions are made up of blocks. So how do we want to show a function? So here's a block, but a function would be a sequence of blocks. Like so. That's basically what a function is going to look like. And it doesn't, right now, doesn't have any other. I think a function should have a name. And should it be a string? I was using symbols before. I like the look of symbols here. And it really doesn't matter. So we're just going to generate this directly, I think. Like we could build it into closure data and then print the closure data, but like, what's the point? Why do that? So we have a name here. And we're going to format that. And then we're going to do our blocks like that. And then we're going to finish our blocks, and then we're going to finish our that, and then we're going to print f. And so we're going to loop through all of our blocks. Functions have blocks. And so we're just going to go auto const block in function dot blocks. And then we're just going to do print on block with the string builder. And then we're just going to have the same sort of function for block. And for blocks just print, so they're a vector as well. So that's going to start and end like so, and then they just need to loop through their instructions. And so what do we want to go here? We want b dot instructions, and then we're just going to print that, and then we need a print for instruction. instruction and now instructions are just maps. And so we'll need to do a switch because we have a variant. We'll need to do a visit. I always forget because boost visit and standard visit swap the orders of the variant and the function. Yeah, so boost visit puts the variant last, and then here we actually put the variant first. So we call that data. Data, we're going to visit that, and then we're going to visit that with a function, which is generic C++ lambda, and we're going to call that typed data, and so we're capturing by reference because we need to capture the string builder in order to have that work. And then here, I think what we'll do is we'll just do a if const expression. There are other ways to do this, but this works. So if const expression and then same as, and then so we have literal and ret. So inst literal, and so here's like C++ 20 at work. The dum bum bum with this if const expression. So in these cases, so in the case of literal, we had it like so. Name, literal, and value. So let's just do that. So I'm just going to grab this to build from. And so this was name and then op, literal, and then value. And we're formatting that in. So we're going to have typed data name and then typed data value. Yes, but value is a runtime object, so we need to do a runtime to code string to get that. And then for ret, we'll do the same thing, except we don't have value, so we don't need to worry about that. And then save, allow that to format, and then see what kind of errors we have. So we need to include jank util format, I think it's called. I don't know what's up with my LSP right now. I think it's called FMT, and I should really just rename it to format, because like I spell out everything. Yeah, it is. And wait, this says that the variant goes after and the visitor goes first. Did I read that wrong here? Oh, am I looking at the member function? Yeah. That's fine. That is fine. We'll just swap the order. Okay. And so that's saying that there's something wrong, but I'm pretty sure we're actually just missing the include for that. Yeah. Okay, so I have to run in just a couple of minutes, but hopefully what we could do before I go is we can actually print out something. Let's try to do that. So what I'm going to do right here is I'm just going to hack in a return, and then I'm going to grab jank IR processor. Now the IR processor requires maybe there's a better place to do this so that we will already have all the information that we need. All right, let me undo that and then run evaluate. Let's do that right here. So wait, whoops. Let's put this here and then let's do an IR processor. Oh wait, we don't actually have that. We just have this function called IR create. Let's do that. So IR create, and that takes in the expert, takes in some module, also takes in a code gen compilation target, which we're not currently bothering with. So I'm just going to give any value there. So all that compiles and links, which is great. And then if we do a jank run, so this is going to happen when we do a eval of functions. So presumably, if we just did a function here that returns 42, and we try to run that, and then we go into here, and after we build our function, we print our function. And then does print take a string builder as well? Yes, it does. So we make a JTL string builder SB, and we pass that in. All right. And then our question is, why is this not ending up here? We should eval the function, Are we getting to our function? Yes, we are. Arities. Good. So if we step over this, we step over that, we step over that, we don't actually print. Okay, let's start again. So we're getting the right place. blocks in place back. So p function blocks dot size is 1. Good. And then so builder, where was I? Here? Actually, builder is defined in here. So the builder has just a block. So let's do builder.block.data. Good. Okay. Now, if we step into this, fine step, we take our block instructions and place back. Good. P block instructions dot size 1. Good. Step into this. So we have our block. Good. Step into the block. Ah. So I formatted it to the string builder using this print here, but we didn't actually print it out. So I think that was the problem. We did our string building, but we didn't actually write it out to the terminal. Nice. So our function doesn't have a name, and that is okay. We can just say function name. Oh. We have a bit of shadowing going on here. So function name is function expr, and this has a name right here. So this has a unique name, and we'll need to deal with the arity suffix on that as well, but that's okay. And then we have our blocks, and here we end up creating, this says literal. Did I not do the correct thing? Yes, I did not do the correct thing because that should be a ret. Nice. So now we have a function with a name that has blocks, and it has one block, and inside that block we have one instruction, which is returning some name foo. Now foo hasn't been defined yet, but if we wanted to, then we extend the builder, we add a literal function, and then we can introduce the name. So if we do a literal, we have a name, we take in a runtime object ref value, we create a literal with the name, with the value, and then all we do is this literal foo 42. Wait, make box 42. And then I'm going to need runtime core make box. And I need runtime on that, I think. Where was that? Right here. Yeah, so here we can create a function and we can create a set of blocks, and then inside of the first block is going to need to have a name. Like, we need to name the blocks as well. Yeah, so we'll need to turn the block into a map that then has a name and then instructions. But yeah, we have an instruction to load the literal 42, put that into foo, and then instruction to return foo. So this is the start, right? This doesn't actually, like, all this is just kind of made up right now, but like we're not far off not making this up. All we need to do is just start plugging the values from the AST into this. Hey Cam. No problem. No problem with you being wherever you've been. I hope that you've been great. And I hope that you've come back even better. Sorry to run when you just dropped in, but I was telling the other folks I have an appointment I need to get to. I was actually planning on ending 10 minutes ago, but I wanted to get to the point where we could actually see the fruits of our labor by printing this out. I mean, very humble beginnings, but Cam, we're doing a whole new IR internal representation in jank that we're gonna then use to optimize, and then that's gonna lead to different whole new code generation as well, and hopefully this puts jank in a different category when it comes to performance. And this is. It may seem like not much, but actually this right here, what we have is the foundation of how all of this intermediate representation is going to come together. So I'm pleased in terms of what we accomplished. And I'll keep hacking away on this. Next week when we meet, I will still be working on this, and we'll be much further along, and I'll have a lot more to show, a lot more to talk about. For now, I got to run. I hope all of you have a great day. Looking forward to catching up on my game engine with the latest improvements soon. That's a game engine in jank, right? In which case, fuck yeah. Yeah, there's a lot of great stuff. A lot of great stuff coming out, Cam. But yeah, glad to have you back. Looking forward to you working on that game engine. I'll catch you guys later next week. And we're gonna keep digging into this IR optimization stuff. All right, adios.